Hello, you wonderful little gens out there. It is so great to see you all here today, and thank you for joining me. Today, we are talking about multi-step calculations, which invariably is probably one of the most difficult parts of science. It's usually worth around about 5 to 6 marks for each question, and that therefore will involve multiple equations being used, and indeed multiple rearrangements potentially might be required. So I'm here to help you work through some of the most difficult equations out there and just give you a little bit of support in that, providing you with a comfort blanket of knowledge around yourselves so that when you do go into the exams, whether it be in the November marks or whether it may be in the February or March marks, wherever it might be, or indeed, of course, the real thing, just to provide you with a bit of reassurance that you can do it, you can achieve it, and it is possible with a secure foundation of knowledge. And you've got it. Welcome to Sonic Science, and I am Mr. Soni. I've been in education for now 23 years, and I have a national role in science education, training teachers up and down the country in the lovely discipline of science. So it's my real pleasure to be with you here today, and I just hope that I can help you out a little bit. So without further ado, buckle up, and we're going to get into it. Let's go. Okay, folks, so I use a technique called ESRA, so equation, substitute, rearrange, and answer. The reason why I do it that way is only so that you don't forget to substitute the numbers into the equations, which you will get a mark for, even, of course, if you get the wrong answer. But you have different techniques of doing it. You could do ESRA, which is equation, rearrange, substitute, and answer. But the preferred method is the ESRA method because it's clearer and the substitution is done from the outset. I will go through how to find out the most appropriate equation for the question. We're going to find out how to best use those particular equations. I am focusing mainly on combined science content, though obviously there's crossover with separate sciences. And it's important to note that for this video, I'm going to focus largely on the equations that come about in the energy topic, which is physics topic 1. And all of the questions that I'm going to be providing you with are all grade 7+. Everything I'm really going through today is higher tier, but of course, if you want to learn more about how to possibly be equipped with the knowledge to change your tier, if you want to upskill yourself in being able to do that, then this is the video for you. Do feel free to pause the video at any point at all because it's really important that this is for you. So pause the video, try the questions out. I hope the questions are nice and clear for you. And then if you then want to allow me to go through that, then of course unpause and I will go through the working answers with you, showing my working out and showing my calculations according to the method I mentioned earlier. Just a reminder, if you've got a 6-mark question, you need to allocate 6 minutes to do that. So as you pause the video and you work through that, please be mindful of the fact that you should also be adhering to that particular time limit as well. Lots of word examples on the way. Please feel free to comment in the comment section below. If you like the video, then of course subscribe because I'll be making more videos like this as time goes on. I'm really looking forward to your learning experience. Enjoy, everybody. Okay, let's have a look at this question. So the current in the lamp is 0.21 amps. When the potential difference across the lamp is 6 volts. So you know you're working with the figure 0.21 amps and you're working with the figure 6.0 volts. Calculate the energy transferred by the filament lamp in 30 minutes. Now, straight away, you know this has got to be converted to seconds because time in science is always measured in seconds. So you do 30 times 60, which will give you 1,800 seconds. Great. Okay. Now, I always use a technique called ESRA, where you write the equation, you substitute the numbers, you rearrange if necessary, and you write an answer. So let's have a look at what kind of equations I'm going to require here. So I've got as I said, I've got my current and I've got my voltage, and straight away the formula that links the current and the potential difference is this power equation here. So power is equal to potential difference times current. Now, looking at the second part of this particular equation, you can see calculate the energy transferred by the filament lamp in 30 minutes. So you've got the time and they're asking you to work out the energy transferred. And from these two values here, you're going to work out power. So the formula that will link power and time together is this one down the bottom. So it's energy transferred is power times time. So let's get cracking with that and let's work this out. So the equation that you're going to require here is power is equal to potential difference times the current. So power is, potential difference is 6 and the current is 0.21. And so you know that 6 times 0.21 is what you're going to have to plug into your calculator to work out power. Now, note to you all is that remember, you must substitute the numbers in order to be able to gain a mark for this particular part of your equation. Okay? So make sure you've substituted those numbers in because that will give you a mark in the exam. Rearrangement wise, you don't need to rearrange anything because the variable you're trying to work out is power, and you know you've got to times those two numbers to be able to get it. So there's no rearrangement required there. So you just put an X there, as I've just done. So now I'm going to plug in my my numbers into my calculator, and you can see 6 times 0.21 will give you 1.26 watts. All right, so now I've got my power. Great. So the second formula I'm going to need here is, I'm going to need, as I said to you earlier, energy transferred is power times time. My power, as you know, is there. So energy transferred is power times time. And I'm going to substitute my numbers in. So energy transferred is equal to power, which is 1.26, times time, which is 1,800 seconds. And then I'm going to rearrange it if necessary. I'm not going to need to because not required. So just put an X there. And now I'm going to put in the answer. So 1.26 times 1,800 will give me a figure of 2,268 joules. And that is what will go into here. And that, folks, will give me my 5 marks. Right, so let's have a look at this particular question. So, figure 13 shows part of a mains electricity lighting circuit in a house. You've got a neutral wire feeding into a lamp. Then you've got a switch, which is open, and then you've got a live wire here as well. So, a fault in the switch caused a householder to receive a mild electric shock. God, I do hope they're okay. Before a safety device switched the circuit off. Okay, brilliant. Thank God for that. The mean power transfer to the person was 5.75 watts. So the power going to the person was 5.75 watts. All right, brilliant. The potential difference, or voltage, across the person was 230 volts. Calculate the resistance of the person. Right, so we've got our power, we've got our potential difference. We need to work out resistance. Right, something is missing there. Let's have a look. Okie dokie. So, hopefully you guys can see that. There we go. So we've got power, we've got potential difference, we need resistance. So in terms of power, power is potential difference times current. So we've got power, we've got potential difference, we've got power there, we've got potential difference there. But doing something with this formula will give me the current. Now, I know I'm going to need to use the current in terms of being able to work out resistance. So let's go with this particular formula. So we've got current, which can be used here. We have the potential difference here, which can be used here, and we can do something with those two numbers to work out the resistance. So I know I'm going to need this formula, and I'm going to need this formula here. All right, so here we go. Let's do it. So let's start with the equation, which is, our first equation was power is equal to potential difference times current. All right. So now let's substitute our numbers in. So we've got our power, which is 5.75 watts, is equal to voltage, which is 230 volts. And we know that that is times current, but we don't know what our current is yet because we haven't worked it out. So now it's time to rearrange. So you know that we're trying to work out current. Now, remember, whenever I rearrange, I always write the symbols out because I think that's really important to do that in terms of working out what it is and how to rearrange that particular equation. So I am going to rewrite that. So it's power is equal to voltage times current. I'm working at current. So I'm going to put a circle around the current. Now, remember, current is next to voltage in this equation. So they are currently being multiplied, no pun intended. To cancel out a multiplication, you need to divide it. So if you divide this side by V, V would cancel V, and that would leave current there by himself as the subject. Whatever I did on this side, I need to do on this side. So I divided this side by V, so I need to divide that side by V as well. So when I rewrite that equation, it becomes current equals power divided by voltage. So now I've got my ways and means to work out my current. Brilliant. Wonderful. Now I'm going to plug in my numbers. So So current equals power, which is 5.75, divided by voltage, which was 230 volts. And then when I've done that, folks, that will give me my answer, which is 5.75 divided by 230 gives me 0.025 amps. Wonderful. So now I've got my amps. Brilliant. Lovely. Lots of thumbs up here. Very, very happy with that. So 0.025 amps. Brilliant. Right. I'm really happy with. So now we go to my second equation. Calculate the resistance of the person. So we're going to have to use something that is going to involve resistance. Here we go. So potential difference is current times resistance. Potential difference. So potential difference is current times resistance. Brilliant. All right. Now let's substitute. So it's going to be 230, which is our voltage, is equal to current, which we know our current, where are you, is 0.025 amps. And we're going to times that by the resistance. But of course, we don't know what the resistance is. So we're going to have to rearrange the formula. Now, remember, for rearranging, I always write the formula out in terms of its symbols. So voltage is equal to current times resistance. I'm working out resistance. So remember, the resistance is next to the current in this equation. And so in order to get rid of a multiplication, you need to divide. So in this case, you will divide that side by I. So I will cancel I, leaving R by himself. And whatever I did on this side, I need to do on this side. So because I divided that side by I need to divide that side by I. So when I rewrite this particular equation, it'll be resistance equals voltage divided by current. Lovely. Now I'm going to plug in my numbers. So it'll be resistance is voltage, which was 230 volts. And we know that from here. Divided by the current, which we know was 0.025 amps. And when I plug that in to my calculator, it will give me 9,200. And the unit is already given there. It is ohms for the symbol for resistance. And so that, folks, is our answer for the full 5 marks. And now we come to the absolute horrific question that will probably break you out in hives and definitely causes anxiety for folks, but it is absolutely okay. We can deal with it. We are skilled enough to be able to tackle it. So let's have a look at the question. The condenser transfers energy from the coolant to the air in the building. When the total energy input, so the amount of energy going in, to the heat pump system is 1560 kilojoules, straight away I know that that's going to have to get converted to joules. And so 1560 kilojoules is 1,560,000 joules. So when the total energy input go to the heat pump system is 1.56 million joules, the temperature of the air in the building increases from 11.6 to 22.1 degrees C. Now, the difference between those two is 10.5 degrees C. The efficiency of the heat pump system is 87.5%. So the efficiency is 87.5%. The mass of the air inside the building is 125 kilograms. Calculate the specific heat capacity of the air in the building. So straight away, you know you're going to have to work out the specific heat capacity here. Right. Now, what are the equations we're going to require? So when looking at this, I have, let's have a look. So definitely specific heat capacity. So I'm going to need the specific heat capacity formula here. So change in thermal energy is mass times specific heat capacity times temperature change. And they're asking me to work out this little baby here. Now, they're also giving me the efficiency. So they've given me the efficiency. And so I've got efficiency is either useful output energy transfer divided by total input energy transfer, or useful power output divided by total power input. Now, I'm not dealing with power because nowhere in this equation or nowhere in this question does it mention the letter W for watts. So I know we can discount that one completely. I don't need that one. But I do know that I'll need this one. Okay, so I now know that I'm going to be using this particular equation and this particular equation here. So I'm now going to start by working out my efficiency, or in fact, using the efficiency equation, which we know they've given me the efficiency, which is 87.5%. So efficiency, and I'm going to write just efficiency here, is useful output energy divided by total input energy. All right, so I'm going to go rogue here, and I'm going to go useful divided by total. All right, now though technically that's not how you would write that out, but I'm just doing it short form for ease of understanding here. All right, so now I am going to be substituting my numbers. So efficiency we know was 87.5%. Now 87.5% as a decimal is 0.875. All right, so I'm just going to convert it to a decimal because that is the way that it needs to operate. And we know that efficiency is useful energy divided by total. We don't have useful, but we do have the total because the total energy input to the heat system was 1,560,000 joules. So equals useful, which we don't know, but divided by total, which is 1,560,000 joules. All right, okay. So hopefully that's making sense so far. All right. Now I need to rearrange this to work out U. And before I do any rearranging, I always write the original formula down. So efficiency is equal to useful divided by total. I'm working out useful. You can see U is divided by T currently. So the way that you would isolate U by itself in mathematics, you have to do the inverse. So this is currently divided. So you therefore do the inverse, which is you multiply it. So T multiplied by T cancels each one another out. And whatever you did on this right-hand side, you need to do on the left-hand side. So because you multiplied that side by T, you need to multiply this side by T. All right. So when I rewrite that, so it'll become U is equal to efficiency times T. Efficiency times T. That's why I've written it like that. Now, when I plug in my numbers into this, obviously, I am going to have, let's write it here. So U is equal to efficiency, which is 0.875 times T, which was 1,560,000 joules. Okay. So that will give me my useful energy input. Now, when I plug that into a calculator, it will give me the answer, which is 1,365,000 joules, right? That is my useful energy from this particular equation. Right, so now I've got my answer. We now know what my useful energy is. Now we need to use our second formula. And our second formula is change in thermal energy is mass times specific heat capacity times temperature change. We are working at specific heat capacity. So now I've got my change in thermal energy, which is this figure here. We will be able to work with the formula in front of us. So let's put a little line under that. Now let's write our equation out, which is change in thermal energy is equal to mass times specific heat capacity times the temperature change. Now, substitute our numbers in. So in this case, we've got the 1,365,000 joules as our energy there. And that is equal to mass. What's mass here? The mass is 125 kilograms. Times the specific heat capacity, don't know what that is yet, so we've got to leave it as is, times the temperature change. And the temperature change was from 11.6 to 22.1, which was 10.5. Okay, so now we need to work out our specific heat capacity. Now, as I always say, in order to rearrange, I always work with the original formula first. So we've got the energy transferred there is equal to the mass times specific heat capacity times the temperature change. And so when I want to work out the specific heat capacity, You can see specific heat capacity is next to mass and next to change in temperature here. So they are being multiplied currently, and the inverse of that is to divide it. So in order to leave specific heat capacity by itself, you need to divide this side by m and temperature change, or mass times temperature change, and in which case mass will cancel mass and temperature change will cancel temperature change, leaving C, or specific heat capacity, by himself. Now, whatever you did on this side, you need to do on this side. So what you did, you divided it by mass and the temperature change, so you need to do the same on this side. So you do mass and temperature change. And so when you rewrite that, it becomes specific heat capacity equals energy transferred divided by mass times the temperature change. Brilliant. And now I'm going to plug in my numbers. So C equals the change in energy, which was 136,500, divided by my mass was 125 kilograms. My temperature change was 10.5 degrees C. And so now I'm in a position where I can work out my particular specific heat capacity. I've just put brackets around that because obviously it is an additional calculation that you need to include. Now, when I plug that into my calculator, that will give me the answer. I'm going to put the answer down here, which is 1040. Now, if you notice, give your answer in standard form. 1040 is 1.04 times 10 to the power of 123 joules per kilogram per degree C. Right. Congratulations. Well done for surviving that one. That is absolutely horrendous. But if you were able to do it, brilliant. Really proud of you. Well done. But that definitely was the trickiest part of today's session. Hopefully, you found that useful. A big thumbs up to you all if you got it right. And if you didn't get it right, that does not matter. The point is, were you able to work out how and why you might have got it wrong? All right? So don't chastise yourself. You be kind to yourself, and you know, if you couldn't do it this time, you will do it next time, because of course you've got a model in front of you now. I really hope you found that video incredibly useful. As I was saying earlier, please endeavor to like and subscribe. If you would like more videos on this, I've got another video which I've just recorded, which is all to do with power and electricity calculations. So please endeavor to check that out over here, and I look forward to seeing you in that video in due course. Take care, everybody. Good luck, and I will speak to you soon. Bye-bye.